Scusa, dov'è? Dove lo devo vedere qui? Ah, ok. Allora, ci siamo. Allora, posso avere la vostra attenzione per cortesia, per la prima volta siamo in streaming. Io ringrazio le persone che sono intervenute e le persone che ci stanno intervenendo via streaming. Let me switch to English and close the telephone, otherwise we have the noise. And well, this is the first experience, the first experiment, and I thank Vadim Kaloshin to be the pioneer of this series of seminars which are given via streaming. And we hope to improve the technology in the near future. So Vadim Kaloshin from the University of Maryland is a leading expert in dynamical systems and in a lot of areas in dynamical systems, from Hamiltonian dynamics to celestial mechanics and Arnold diffusion and Hamiltonian degrees and so on. So he got a PhD in Princeton. He was invited to many international meetings, and he was even in the selection committee of the ICM 2010, if I remember well. And his position now is at the University of Maryland, and he has the microgreen chair at the University of Maryland. So it is I'm very happy to welcome you in Tor Vergata, and I kindly ask Alfonso to chair the session.
Okay. So it's our pleasure to have Vadim Kaloshin from the University of Maryland to talk about stochastic Arnold diffusion and deterministic conferences.
Thank you very much for such a generous introduction and for the invitation. It's a great pleasure to be here. In my talk, I will discuss some hopefully interesting properties of Hamiltonian systems, and I will start with a short BBC video. So there is an astronomer and mathematician Jacques Lascar who wrote a huge program, and this program could integrate motions of planets in the solar system for a long time. And basically what he did after he wrote this program, he picked 2,000 initial conditions for the solar system. It includes Sun, 8 planets and the Moon. And for these 2,000 initial conditions, he ran numerics. And what he found out that in roughly 10% of the cases, there was a disaster happening. And in the 90% of the cases, some nice things were happening. So maybe I'll tell you about, the BBC will tell you about a little disaster which was happening in 10% of the cases, and then I'll start mathematical part of the talk.
Astronomers used to think that the planets in our solar system would follow fairly predictable orbits. But 20 years ago, researchers at the Paris Observatory worked out that there were tiny fluctuations. Now they've produced this simulation, which shows what happens when these fluctuations grow. Now, here's the Sun, here's Mercury, here's Venus, here's the Earth, and here's Mars. Now, the key figure to keep your eye on is this one. This shows time thousands of years ahead in the future. Now, as the time increases, you can see that these orbits become more and more unstable. After a few million years, you can see that the orbits start overlapping. Here, Mercury is overlapping with Venus, so that increases the possibility of collisions. Now, after 3.3 billion years, there's a chance that Mars might collide with the Earth, and even Venus and the Earth might collide. And this is the moment we've been waiting for billions of years. Mars crashing into the Earth, complete devastation to both planets. There might even be a near miss. And in this simulation, Venus crashes into the Earth. But fear not, this is unlikely to happen for at least 1 billion years.
Okay, so maybe you saw this nice video, and first there will be 2 basic questions which I want to address during the talk. The first one is when fluctuations grow, and as you saw, if fluctuations grow, it could lead to this exciting picture. And the second question which I want to address is when a system, a dynamical system, exhibits mixed behavior. And I will address these questions a little later. So now let me go back to the talk and okay. So it's the talk. So the talk will be divided into 3 parts. So the first part is an introduction. So basically, in the first part, I will formulate the class of systems which I would like to investigate, and the main one of the main reasons these systems turned out to be very interesting is because about 100 years ago there was a general belief that if you start with a dynamical systems, then behavior of a generic, in some sense typical dynamical system preserving some measure has to be ergodic. And one of the reasons so-called Hamiltonian systems became very interesting because it turns out that the idea of ergodicity fails. I'll get back to the idea of ergodicity later on, but basically idea of ergodicity is that orbits of a typical dynamical system are free in choosing the type of motion unless there is some serious restriction. So basically, it turns out that there are classes of Hamiltonian systems for which ergodicity fails, and those classes could be described as integrable or nearly integrable system, and I will describe those. And this is basically the class of systems I will be studying. I will be studying systems which are very close to so-called integrable systems. And it turns out that for those systems, there are conjecturally at least 2 types of behavior. So one type behavior is very regular, almost periodic, and relatively easy to describe. And this is due to KM theory. And another type of behavior is a diffusion behavior. And that's where you will hopefully see mixed behavior. So basically, it turns out that these kind of systems, they exhibit chaos in some places and very nice deterministic, almost periodic behavior in other places. So this idea of mixed behavior is something which I will try to emphasize, so that there are classes of dynamical systems, Hamiltonian systems, for which complete chaos and almost periodicity can take place. So this is kind of the first motivational part of the talk, where I will talk about what kind of objects I'm going to study and what I'm going to look for. And after that, I'll get closer to the video which you saw in the beginning. Namely, I'll get to example in the solar system. So in the solar system, between orbits of Mars and orbits of Jupiter, there is a very interesting region which is called asteroid belt. And in this asteroid belt, there is more than 1 million asteroids. And the point of view which I will choose is I will be looking at 1 million solutions to a certain differential equation or a certain dynamical system. And it looks like, it turns out that when you look at the various distributions in this asteroid belt, namely at these 1 million solutions, then one type of behavior which you see is almost periodic behavior, at least mathematically. So very nice, well-ordered behavior. However, if you look at if you look at some peculiar places in the asteroid belt, then you will see stochastic behavior. At least you can see this numerically, and there are some heuristics about it. So this would be a first example of a mixed behavior where, roughly speaking, more than 90% of asteroids behave in a very deterministic, almost periodic way. And then there will be a small fraction which will behave, so to say, chaotically. In this second part of the talk, I will not give you results, mathematical results. I'll just give you results of numerical experiments and what you could find in Wikipedia. And after that, I go to third part of the talk, and in the third part of the talk, I'll show you a concrete mathematical model for which we've managed to prove coexistence. Namely, the main result will be that for some nearly integrable Hamiltonian systems, roughly speaking, 99% of the orbits behave in a nice, almost periodic way. But among those 1% of other orbits, there will be some stochastic behavior, and this will be stochastic behavior in the sense of diffusion processes. So the rough plan is introduction to motivate why I care about this class of dynamical systems, give you a first example for which is very exciting and you could see it in the real life. But here there will be only numerics, and then I'll give you mathematical results. And in the future, we hope that technologies from this model can be applied to the asteroid belt. Okay, so what are the Hamiltonian systems? So it turns out that if you use Newton's second law, then there are some peculiar differential equations which come out from a Newton's second law, which says that the force acting on a body is equal to mass times acceleration. So a slightly more general class of systems for which slightly more general class of systems which obey these rules are the systems of the following type. This is a vector form, so this is 2m dimensional differential equation. And it turns out that for this 2m dimensional differential equation, there is a conserved quantity. Namely, if you look at this R2n dimensional space, and you look at so-called energy surface, where H is equal to E, then it turns out that if you start with the initial condition on the energy surface, it will always stay inside of the energy surface. And as a result, it's definitely clear after this that the orbits, when you restrict to energy surface, you could study the dynamics inside of the energy surface. And for simplicity, let me assume that energy surface is compact, so you don't worry about problems at infinity. So now, what kind of model I have? I have a differential equation, and I could think of this differential equation that I could study energy surface at the time. So this differential equation has another structure which is very nice. It preserves volume, which means that if you start with the ball of initial conditions, and for each point inside of the ball of initial conditions, you solve your differential equation, for example, for time 1, then the image under, say, time 1 map will have the same volume as the one you started with. So you have this system which have conserved quantity, which is energy, and which preserves volume. And as I said, about 100 years ago or more, there was a belief that if you start with a generic Hamiltonian system, then the behavior should be ergodic. So I'll say right away that you should assume something about H to see ergodicity, because if H is a constant function, then, for example, differential equation where nothing moves is also a Hamiltonian system, and it's not interesting. So we need to assume at least something about the corresponding Hamiltonian. So let's assume that it's a nice Hamiltonian not a constant and not satisfying some ridiculous properties. What we hope to see is that behavior is ergodic. So one way to say that behavior is ergodic is that time averages are equal to space averages. And a slightly weaker property, which is useful to remember during the talk, is that when I pick a typical orbit and I start seeing what it does, then at the very least, it should fill my energy surface density. So if you don't know what is ergodicity, just keep in mind the pictures that, for me, ergodicity is when typical orbit fills the energy surface density. Then I would feel almost satisfied that there is ergodicity. So that's a class of system for which this was conjectured, and it turns out that this is wrong. And this is wrong for not one peculiar Hamiltonian, for example, Hamiltonian equal to constant, but it turns out that this is wrong for classes of Hamiltonian systems. So there are Hamiltonians H such that if you shake it a little bit, it will still violate the ergodic hypothesis. And the next 15 minutes, I'll tell you for what classes of system, Hamiltonian systems, this ergodic hypothesis is violated. In particular, you do not have that the typical orbit fills the energy surface density. Okay, so now let me give you the first doubts about violation of ergodic hypothesis arose about 60 years ago in a numerical experiment of Fermi, Pasta, and Ulam. So what was the experiment? They considered a collection of springs. And if for collection of springs, you write down the corresponding differential equation, then it turns out that this equation, all solutions are either periodic or almost periodic. And what I say is literally false, but it can be corrected. So statement which can be corrected is that more or less each point performs a periodic motion. So this one performs periodic motion, that one performs periodic motion, and so on. And what you could view these solutions as solutions on n-dimensional tori, where each particle is on its own circle. And then what Fermi, Pasta, and Ulam they hope that when you add some nonlinear effects, because these are equations for a perfect spleen, then there should be some change. And in particular, if you write down these differential equations literally, then I think for the experiment, n was equal to 32. And then the dimension of the phase space of this n is equal to little n. So the things were happening in a 64-dimensional space for one of these experiments. So as I told you, in this 64-dimensional space, there exists an energy surface which is 63-dimensional. And the shock was that when they look at the solutions of most of the solutions which they could compute, they would just stay close to a submanifold. So they did a number of numerical experiments. I don't want to expand to which extent they saw almost periodic motions, but they saw something which contradicts ergodicity in a very strong way, because their solutions were filling up something which is 32-dimensional, not 63-dimensional, and this is strongly against ergodicity. As I told you, ergodicity is when orbits are free to move, and in particular, they could fill in the energy surface. And that was shocking, and then sometimes it calls Fermi-Pasta-Ulam paradox, or in the terms of the story, which I'll start telling you now, is that there are classes of Hamiltonian systems, and this can be rewritten as a Hamiltonian system for which ergodicity is not true. And there are some hidden restrictions on motion of orbits. And this was realized by mathematically by KN theory. So this particular model, it took some years to prove because of degeneracy. And now I will try to discuss in details what are those additional restrictions. So it looks like we have a typical differential equation in some sense, and we hope that the orbits are filling something of four-dimension one or filling energy surface, but they are not. And let me describe this phenomenon of hidden restriction or hidden confinement for the classes of systems. Okay, so let me now also discuss some notion. So it's been realized that, numerically and mathematically that it's not feasible to study individual solutions of a differential equation, because for no practical purposes you know your initial condition exactly. So you never know your initial condition with absolute precision. You always know your initial condition with some error, and it turns out that when you just even make a tiny error in your initial conditions, as Laskar did, then you have hard time saying what the actual solution does. So the point of view which we will try to promote is that we look at some region of the phase space. So, for example, on the manifold or in Euclidean space, and what we will do in this region, we will put a grid of points. Like for numerical purposes, people look at grid of points where it is interesting, and we will study then statistics of the evolution. For example, you take 1 million initial conditions at the place where it is interesting, and then, like Laskar, out of this 1 million, we will integrate all these solutions for a long time, and then we will do some statistical analysis. 5% of orbits do this, 5% of orbits do that, and so on. So what we will be interested not in analyzing a particular solution. We will be interested in analyzing ensembles of solutions. And if you make this goal a little bit more general, then you could talk about not choosing 1 million initial conditions, but you could talk about choosing a probability measure of initial conditions. And then we are going to run probability measure with solutions of this differential equation and see what happens. For example, Laskar did a measure where he had 2,000 points and he put a measure on 2,000 points, and then he integrates it in time and see what happens. And this is what we are going to try to do for our systems. Because as I said, telling what is the exact initial condition, for example, of a solar system, it's absolutely hopeless. You don't know what it is. Okay, so when we will be studying this differential equations, we'll try to study ensembles of solutions, and we will try to understand those ensembles of solutions simultaneously. Okay, so now let me go back to something which was violated. So what was violated? It was violated, at least on a conjectural level, that when you start this Hamiltonian system, and you hope that almost all orbits behave in the same way, where almost all orbits behaving in the same way, you could view it naively that almost all orbits fill the energy surface density. So this was a hope 100 years ago, but as Fermi Pasta Ulam saw, and then later theorems proved, it's actually not true that all orbits behave in the same way. We put a less restrictive attitude now, and we say that the system has a mixed behavior if there are at least two boxes of orbits. So for one collection of orbits where you have one type of behavior, and for another, for a second group of orbits, you have a different behavior. Then we say that there is a mixed behavior, and as you will see, at least for some classes of systems, we see indications that there will be at least two types of behavior, one which is almost periodic, and another one which is stochastic. So basically, we will try to justify, at least to some extent, that systems of this type, they should have a mixed behavior, and they should have a mixed behavior which you cannot destroy by changing the Hamiltonian a little bit. So now we are studying Hamiltonian systems, and we'll try to establish mixed behavior. Okay, so let me try to describe explanation of Fermi-Pasta-Coulomb experiment. And in order to describe explanation of Fermi-Pasta-Coulomb experiment, I need to describe the classes of systems which I will be studying. And what I will be studying so-called integrable systems. And at first, the definition would look really peculiar. So the definition would say that my Hamiltonian system is integrable if there exists some very nice coordinate system such that in this very nice coordinate system, the equations of motion are as follows. So where phi is on n-dimensional torus, and usually it's called angle, and I is in some open set, and this is called action. And I don't want to discuss more zone bracket. So as a consumer, what I want to see the following picture. So there are some Hamiltonian systems where all of your phase space consists of these tubes, these tori, and when you take a union of those tori, then they just fill out everything. So if you're, for example, in three-dimensional setting, you could just think of a donut, which is just fully, which you could peel off one torus at a time. And what is exciting about these systems is that on each torus there is a very simple motion. You see, I dot is 0, therefore phi dot is equal to constant, and these are the kind of orbits you get. So you see, this integrable systems is that if you are clever enough to find coordinate system, and this is called action angle coordinate system, then you are in good shape. But a natural question you could ask, well, maybe you're asking for something which is too much to ask. How you could have a system which is so simple that all solutions are just trivial to write down. And it turns out that there is a pretty long list. The list I'll give you is not complete, but if you want, you could Google Wikipedia and you could say integrable systems. And there are many systems of Hamiltonian. All of these are Hamiltonian systems, and I'm writing down the Hamiltonian and just claiming that for this kind of coordinate, for this types of systems, there is action angle coordinates. And as you can see, the list is pretty long. What it tells you that these equations, they have something hidden which separates them from differential equations. And in particular, as you can see, there are classes of Hamiltonian systems which have this action angle coordinate system, mainly a coordinate system with this property. And in this action angle coordinate system, everything is just trivial. And in terms of Fermi-Pasta-Coulomb experiment, I was telling you that each point on the screen makes a periodic motions. You could actually read these periodic motions from n-dimensional torus. So these are integrable systems. And now what I would like to do is I would like to consider perturbation. So let me consider perturbation. So let me consider a system which is h epsilon phi I, and it is equal to h0 of I plus epsilon h1 of phi I. So let us consider a system, and we see kind of a miracle. And so what is exactly the miracle? When we consider this perturbation, then the differential equation becomes of the following type. And now you hopefully start to see small fluctuations. So what are the small fluctuations? We see I dot is no longer 0. So I dot is small. So the I components start to make little fluctuations, and the same as astronomers notice that there are some small fluctuations of parameters of the orbit. So you see, when I make a perturbation, so I naturally tend to think that maybe these little fluctuations, little oscillations of eccentricity could grow, and if they would grow, then it would be at least a partial confirmation of ergodicity, and the shock which both Fermi Pasta-Ulam and Kolmogorov-Arnold-Moser saw is that for many solutions, these fluctuations do not accumulate and they do not grow. So it turns out that you consider this system, which is, for example, you pick any integrable system from my list, and then you slightly deform it by changing the Hamiltonian. I don't know, make a spring which is not perfect, or put into the solar system Jupiter, or make some small perturbation of your system. And what happens is you made small perturbation, but for large fraction of solutions, nothing have changed. So large fraction of solutions turns out to behave exactly the same way as before the perturbation, because before the perturbation, solutions were almost periodic. Now we make a perturbation, and they are still almost periodic, and they fill out n-dimensional torus. So let me maybe show you the picture. So as I said at the beginning, my phase space of integrable system were foliated by this invariant tori, and all of the phase space, so everyone belonged to a particular torus. Now what I'm saying is that you add a little perturbation and you get a little gray area. So between those tori, there will be some little layers where something happened. But for most of the solutions, we have exactly the same picture as we had before. So we made the perturbation, but 99% of the solutions, they don't know that the perturbation is there, because 99% of the solutions, they behave exactly the same as they behaved before, and this is what Fermi Pasta-Ulam saw. So they add some non-linearity, they deform a little bit the Hamiltonian, but 99% of the solutions, they just have, if you adjust coordinate system a little bit, they are the same as they were before, and this was shocking for physicists, is that you see, you add the perturbation, and for most of the orbits, fluctuation of action variables, they do not grow and they do not accumulate. Moreover, in some nice coordinate system, there will be no fluctuations at all. So this is the first type of behavior which I want to describe. Namely, you see, you have class of systems, so which are called nearly integrable. So they are called nearly integrable because you start with something integrable, and then you make a perturbation. And for all systems of this type, 99% of the orbits are the same as for the integrable system. So this is a first type of behavior. Now, you might ask a totally different question. You might ask the question, is anything changed? Because you see, we added the perturbation, and 99% of the orbits are the same as they were before. So you might ask, but maybe everything stayed the same. But it turns out, no. When you add the perturbation, at least something breaks. And let me naively tell you what breaks after I add the perturbation. And now what I want to look at the product space for integrable system, namely, this part. So I want to look at, so I have an angle which belongs to n-dimensional torus. So let me draw this n-dimensional torus. So, and this is where the angle lives, and here is where the action lives. And I want to restrict myself to two-dimensional case. So what turns out is that in your ambient space, there are some surfaces, and close to those surfaces, so this is a hypersurface, in this case, in the 4-dimensional case, in multi-dimensional setting, there will be a 4-dimension one hypersurface, and close to those hypersurfaces, something was ruined. So it is indeed the case that something indeed changed, and I don't want to give a definition now how to describe those surfaces, but there are surfaces where something has changed, and these are the surfaces where we could hope to see that the behavior is not totally deterministic as it was before. And well, it turns out that those surfaces are fairly dense, and maybe if you haven't seen it before, just focus on two surfaces, and I will refer to small neighborhoods of those surfaces of size square root of epsilon as a stochastic layer. And the meaning of this stochastic layer you will understand a little later, but in a very rough terms, conjecturally, in the complement to this neighborhoods in the complement to stochastic layers, you have almost periodic behavior, but inside those stochastic layers, you have some stochastic behavior, and this will be a mixed behavior which we want to establish. So the outcome of KM theorem conjecturally says the following: you consider integrable system, you deform it, and after you deform an integrable system, the 99% of the orbit behaves in exactly the same way as original system, and fluctuations do not grow. But now we want to look at what has changed, and we want to look at these stochastic layers, where we hope to see effect of the perturbation in the sense of creating chaos. And here's a conjecture which goes back to Arnold. So the conjecture says that yes, something have changed. So the conjecture basically says that when you add a perturbation to your system, then something changed. And one way to see it, you want to see whether there exists an orbit which travels distance of order of 1. And in other words, the conjecture says that it is possible to small fluctuations of I to accumulate. So you see, I dot has little oscillations, and Arnold says that yes, it is possible to find an orbit for which small fluctuations of I component will accumulate. And this is this conjecture was expressed by Arnold about 50 years ago, and even though it's only a 5-page paper, it's the most cited paper of Arnold. And so in the case n equal to 3, we wrote a book with Kiazan in proving this conjecture, and there is an alternative approach by Chen and Jean-Pierre Marceau, but we were all heavily influenced by the work of John Mather, who developed techniques to important techniques to prove this conjecture. So even though on the mathematical side we were very happy to prove this conjecture, and I will discuss only the case n equal to 3, but you see, if you start from a point of view of a physicist, it doesn't tell you much. There exists an orbit. So basically what it would tell you, it would tell you that if you put all the planets of a solar system in a very exact solution, that something could happen. Certainly from a point of view of physicists or astronomers or applied mathematicians, if I tell you that there is one orbit which does something crazy, then you won't be really impressed about it. More realistic question would be, show me a region in the phase space where I could take a grid of points and say 10% of those points will do something crazy. Then it would be interesting. And one other thing I want to emphasize is when Arnold constructed an example when this happens, he calls his phenomenon instability, or he called his phenomenon that you could rephrase it that he said that it is possible for fluctuations of action variable to accumulate and grow. But then, this is the 60s, but then in the 70s, there was a work of Chirikov, and the Chirikov designed the term Arnold diffusion. And diffusion is something which is much stronger, and it brings a lot more structure to this phenomenon. So Chirikov said that he did a lot of numerical experiments, and in the very loose terms, he was saying that in these stochastic layers, there is some stochastic behavior. So basically, there is some sensitive dependence on the initial condition, and if this conjecture were true, then we will be getting mixed behavior, because as I told you, in the complement, everything is almost periodic. So towards the end of the talk, I will show you a theorem which we managed to prove indicating this stochastic behavior. But in the loose terms, we managed to find justifications that for some class of nearly integrable systems, 99% of the orbit are almost periodic, and then inside of the remaining 1%, there is a stochastic behavior. And the stochastic behavior in the sense of eta processes, or a kind of a Brownian motion type behavior. So this is the end of the first part. So by experience, I know that many people might have got lost with all the explanations. So the short summary is that there are some systems for which majority is very deterministic and small fraction is chaotic. And now we go to the solar system, where we will see that. Where we will see that there is one big group which is behaving in the right way, and then there is another group which does something suspicious. Okay, here's an example from the solar system, and again, we will be talking about, I don't know, 1 million solutions to a differential equation, and try to say which one do which. So here's a layer between, this is the orbit of, the red one is the orbit of Mars, the outer one is the orbit of Jupiter, and here this yellow stuff is 1.7 million asteroids, and we are interested to know, say, 1 million years or 1 billion years, what will happen to those asteroids. And we remember this last car video, that if a fluctuations accumulates, then a disaster can happen. So we want to see what happens to those orbits. And let's look a little bit more carefully. So this is zoom in, and in the zoom in, now it's a white area, and we forget about other exterior orbits. And it turns out that these asteroids are really, really tiny. So you see, there is 1 million of them. Actually, latest I saw is 1.7 million. And they're really tiny. If you take union of all of them, it's just 4% of Earth's moon mass. So they're really tiny. So I did completely disregard interactions, no interaction between asteroids. And I am investigating this 1 million or 1.7 million solutions. And I want to see mixed behavior. I want to see that fraction of solutions are nice, almost periodic, easy to describe, and another fraction is chaotic. And you know, from at least 1.5 centuries ago, what astronomers try to do, they try to do some statistical analysis of these asteroids. Before I'll get to statistical analysis, let me remind you a little bit how what Kepler observed. So he observed that if you look at the motion of a planet, then if you forget about all other planets, then the motion of a planet is elliptic, and it can be, at least the shape of the orbit can be described by semi-major axis and eccentricity, and which is A and E. And if you know A and E, you know the shape of the orbit. And if you go to Wikipedia, for all the planets, you will know A and E. And our goal, at least numerical goal, would be to try to study evolution of A and E. And A and E turns out to be action variables of the corresponding nearly integrable system. So the question which we want to address now, whether small fluctuations of A and B accumulate or they do not accumulate. And if you go through the equations of motion, then this is what you will see. So in the solar system, so you have the sun, and then we forget about all other influences, and we put here Jupiter. And after we put the Jupiter, then it turns out that a semi-major axis makes smaller fluctuations, and eccentricity makes smaller fluctuations, and we are interested whether those fluctuations grow in time or they do not grow in time. And here's a histogram of asteroids. So you have this 1 million asteroids, and you draw a histogram. And what is this histogram? This is the diameter, or this is a histogram where you grade according to A. So this direction is A. And if you integrate all this, the area of this black stuff, it's going to be 1 million. And then you try to see among these 1 million asteroids, how many have semi-major axis between 2.3 radii of the Earth and 2.4 radii of the Earth, or 3.2 and 3.3. So it gives you a distribution. And what you see is that it's not everywhere the same. So there are places where you have a lot of asteroids, and in other places you have little amount of asteroids. And in this paper of Moser, he says that the reason majority of asteroids are still there because KLM theory tells them have enormous periodic motion. So majority of asteroids have this almost periodic motion as if there is no Jupiter. And let's look at the complement to see the other type of behavior. So it turns out that the gaps in the distribution occurs if period of asteroid is a rational number times period of Jupiter, or there is a relation between semi-major axis of asteroid and semi-major axis of Jupiter. And to some extent, you could think of these gaps as this as hypersurfaces of chaos. So this is one hypersurface of chaos when there is one relation. That's a second hypersurface of chaos. That's a third hypersurface of chaos. So at least experimentally, you see that for some reason, close to those hypersurfaces, something has happened, and out of those million asteroids, a fraction disappeared. So something have happened, and there is a work of Wisdom and Neistat, which gives one explanation for 3-to-1 Kirkwood gap and 5-to-2 Kirkwood gap. So I remind you, this means that 3 periods of asteroid is a period of a Jupiter, and this says that 5 periods of asteroid is equal to 2 periods of Jupiter. But it turns out that this explanation does not work for example, 7-to-3 resonance and 1-to-2 resonance. And in this paper, we did some structure of asteroid belt. And for this structure, we managed to prove that there exists an orbit of asteroid which gets ejected, for which eccentricity changes by a magnitude of order of 1. So we proved that something exists here, but we don't know how many. And now I'll show you some numerical experiments which shows that there is some kind of stochastic behavior in Kirkwood gaps. So what is the numerical experiment that I want to run? I want to put 10,000 asteroids at a Kirkwood gap, and I want to put them in such a way that they have the same initial eccentricity. So basically, suppose this is the initial eccentricity of my cloud of 10,000 asteroids. So this is a condition I don't have time to explain, but this is a condition which means that you are in a Kirkwood gap 1 to 3. So here, this one means that you are in a Kirkwood gap, and this one means that you fix the shape of the orbit of asteroid. and then you run numerics. So it's 10,000 guys. You run for some time, and these are the distributions which you get. So maybe what I try to speculate is that the distributions are, there are some distributions. So what are these distributions? You see, I started with 10,000 asteroids, and I integrate orbits of those asteroids for sufficiently long time. And after that, I look at what is the eccentricity of all those asteroids. You could imagine an experiment. You start your asteroids on an ellipse of the same shape, and then they evolve, and then you ask yourself, how many asteroids whose eccentricity between 116 and 115? You compute the number. 116, 117, you compute the number. And then you look at this distribution, and the conjecture which I want to put out is probably a rephrasing some form of what Chirikov was saying. So I'm saying that the behavior of eccentricity is stochastic, and that eccentricity behaves as a stochastic diffusion process in this stochastic layer. So basically, you could think that eccentricity performs a random walk at a certain time scale. So this is what it looks like on a conjectural level, and we hope that maybe in the future we could prove it for 7 to 3 gap or 1 to 2 gap, that eccentricity behaves as a stochastic process. Meanwhile, semi-major axis stays almost constant for a long time. So, at least on a conjectural level, I am claiming you that you do have a mixed behavior now. So, mixed behavior because I'm telling you that 99% of asteroids have almost periodic orbits, and possibly 1% of others have a stochastic behavior, maybe less than 1%, but it will give you a mixed behavior. The black stuff is almost periodic, regular, integrable, and the gaps are where asteroids have disappeared.
And sorry, what was the time scale which you were showing this picture?
So it's this is tens of millions of years. I'm not very sure what is the exact time scale as mu goes to 0, but this is tens of millions of years. It's for life of the universe. This is almost instantaneous. It's just, and I think in a paper of wisdom, he has some asteroids which do it in 200,000 years. So just almost like the speed of light by the time scale of the solar system.
Sorry, and mu is 10 to the minus 3.
Yeah, 10 to the minus 3.
EJ is the
5%. 5%. So it's I think it's 4 million. Okay, so that's an example where numerically you see mixed behavior, and let me go to the model which we want to study, and this is so-called Arnold's example. So what we do something which seems really simple. So there is one system for which the solutions are just periodic. So, and this is called rotor. And then there is another system, and you see all the orbits are just circular. And then there is another system which is a pendulum. And what we want to do, we want to add a coupling. So after you add the coupling, KEM theory tells you that 99% of the solutions will still be almost periodic. And what we would like to see, where these hypersurfaces are, or where the stochastic layer is. And it turns out that you start some heuristic analysis. So what is the most unstable solution of the pendulum? The most unstable solution of the pendulum is upside down, because upside down, any little kick and your pendulum will fall off, and these are the corresponding unstable equilibrium of the pendulum. And now it turns out that anywhere close to this orbit, where in the past you go up vertically, in the future you go up vertically, there is an instability, and it turns out that the stochastic layer is an epsilon neighborhood of these orbits. So epsilon close to the orbit, which is in the future becomes vertical, and in the past becomes vertical, is a stochastic layer. And this is where we hope to find some instabilities. Moreover, KM series says that don't look for serious instabilities in the complement. So basically, if you look at epsilon neighborhood, that's where we are going to look for instabilities. And I should say that what we are looking for, we add now perturbation, and we are looking for fluctuations of R. And we are trying to see whether fluctuations of R accumulate. And what Arnold conjecture in this setting says that there are orbits for which fluctuations of R accumulate to a magnitude of order of 1. And there was a long list of people who contributed to solving this conjecture. And now let me show you some numerical experiments, and I'll give you the main result. So numerical experiment is to choose a lot of initial conditions with the same R action. So I fix R. For example, you choose the same R. And then what you want to do, you want to look at what happens with evolution of cloud of orbits which has the same R. So I want to look at small fluctuations of R in the stochastic layer. And this is some a bunch of orbits. So the green orbit, these are fluctuations of R, and the red orbit, fluctuations of R, and the blue orbit, and the violet orbit. So you see, kind of the R component does behave stochastically, but my goal is not to try to find an orbit. My goal is try to find a cluster of orbits, or try to hopefully try to say that there is indeed stochastic behavior with stochasticity with respect to initial conditions. And here's a histogram of taking 1 million orbits with the same R. So this, you take 1 million orbits with the same R, and then you run for a certain amount of time. So it turns out that for many orbits, one loop around the separatrix takes a logarithm of epsilon time. So this is how one loop here takes. And it turns out that R makes random jumps of size epsilon after each loop of R. And what these pictures indicate is that for R, indeed, every turn of the pendulum, R makes a jump of size epsilon, and we want to see how those jumps of size epsilon, how they accumulate. And here's a theorem. So you add the perturbation, which is a trigonometric polynomial. So at the moment, we cannot do better than that. And then I'm telling you that I want to prescribe the range of parameters of those polynomials. So you are allowed to choose, here's a space of parameters of trigonometric polynomials, and you are allowed to choose from there. So you choose the polynomial you like, and what I do, I'll tell you a bunch of orbits. It's actually infinite, and so I'll tell you, here's a bunch of orbits. And I put a probability measure on it. And this bunch of orbits is such that, that they all have the same R component. So they all start with the same R component. And then I take the push forward of this measure. So you could think that I start with 1 million initial conditions with the same R in the stochastic layer, and I let it evolve. And it turns out that the distributions which I will be getting distributions of a stochastic diffusion process. So maybe I'll explain the notation. So this is a so-called white noise. So if you oversimplify the picture and you assume that there is no drift, let's close this term. Let's assume that this is constant. If this is not present and that is constant, I am telling you that the distribution of R will be the normal distribution. So when you will draw the distribution of the R component, it's going to be the normal distribution. You didn't see it very much over here. So you see these distributions do not look normal. So in order to consolidate, at least on heuristic level, these distributions with what we see in reality, you need to add a possibility of having Brownian motion of varying speed, which is this one. It's a Brownian motion with a varying speed and some drift. And it turns out that the drift should be there. So basically, at least in some sense, we show that yes, R component does behave as a random process or as a stochastic process. The only restriction is that I should prescribe the set of initial conditions. So if you give me the right to prescribe the set of initial conditions, then I'm telling you that out of this set of initial conditions, behavior is stochastic. And this is a precise mathematical statement in what sense is behavior is stochastic. And so my time is running out. So the proof of this theorem is more of a book than of a paper. So there are 3 papers on arXiv devoted to so-called non-resonant case. And there is 1 paper which we hope to finish in a couple of months. So maybe I'll just make some comments about this theorem and I stop. So on a conjectural level, what we see a mixed behavior. This system is nearly integrable, and the mixed behavior is that 99% of the solutions behave almost periodically and almost periodically as there were no perturbation. But then there is a fraction which we don't know how big it is, but we managed to prove that there is a fraction of solutions which behaves as a stochastic process. And to the first approximation, you could say they behave like a Brownian motion. The R component behaves as a Brownian motion. And we hope that the technology which we are developing would work for the Kirkwood gap. And then for the Kirkwood gap, we could say that in Kirkwood gaps, eccentricity behaves as a Brownian motion. And it would have been quite remarkable because you start with Newton laws. Newton laws have no randomness whatsoever. And we are starting with Newton laws, and you're producing something which is stochastic, depending on where you look at your solutions. And other aspects of this work is Hamiltonian systems are exact, and when something is exact, you do not expect to have any kind of drift, because there is a law of conservation of energy. But we observed doing a proof where we did observe a drift, and this drift was observed also by physicists, and it turns out that this drift is due to resonant nature of the process, and it turns out resonance is repels the orbits. So my time is up, so maybe I'll just stop here. Again, the 3 papers where the non-resonant behavior is studied are on arXiv, and you could just look at the last names of authors. So maybe I'll stop here.
Any comment or question?
I have a question, which is among Kirkwood gaps, there is the most important one is the 2-to-1, which is also common to other systems like modern system mechanics like suction rings or even the spinal problem and so on. So are you able to cover also that resonance or not? It is
Okay, so
most,
you need to compute a certain phase product of a certain average Hamiltonian, but there is a paper in astronomy which, when I read the description of what they say, I believe that what they say is what we see for Arnold's example. So basically, if what I read in that paper and understand, then the mechanism is the same as here. And the mechanism here is pendulum makes a loop, R makes a random jump. Pendulum makes a loop, R makes a random jump. So I believe that in Kirkwood gaps, at resonances, there is a hidden pendulum. Pendulum makes a loop, and eccentricity makes a random jump. So I believe, yes, it is the mechanism, but we don't have a proof now. So yes, I mean, they explicitly say that 7 to 3 is one of them. They say 7 to 3 and 2 to 1. They say that this one and this one should exhibit random fluctuations of eccentricity accumulate. That's what they say.
I have a question. So you said in the statement of the theorem that the system measure mu epsilon. Can you say anything more?
So this, maybe I'll become a bit more technical. So this measure is actually supported on normally hyperbolic lamination. If you're considering time one map of the system, it's a 4-dimensional symplectic map. So we construct a normally hyperbolic lamination, which is a horseshoe in one pair of variables and a cylinder in the other pair. And the measure is supported on this lamination. So I'm oversimplifying, but you could think of a Bernoulli measure on a horseshoe. So maybe at some point in the future, we could say that this is a Lebesgue measure inside of the stochastic layers, and it's going to be a big victory. And then we could say, yes, it is a mixed behavior, but not at the moment. So at the moment, it's a measure on a carefully chosen horseshoe processing.
Any other comments?
Could you hear some results also about a priori stable states?
So this is a future plan, and I'm not sure what is more difficult, Kirkwood gap or a priori stable, because at least away from resonances, in my paper with Bernard and Zahn, we exhibit a priori unstable structure away from resonances. So it's distorted. But yes, we see it. Topologically we see this picture. We see this picture topologically. So maybe, but you see, there is Mikharoshev stability. So time scale should not be polynomial. So time scale should be quite different. Yes, we hope it is an explanation that away from resonances. At resonances, in a proper time scale, there should be diffusing behavior, but we don't know how to prove it at the moment. Take away from strong resonance.
More questions? So let's start.
Facciamo versione collegate? Si può fare?
Sì, si poteva.